Welcome back, everyone, to the deep dive. Today, we're going to be tackling something that might seem kind of, I don't know, abstract at first.
hmm
It's all about fluid dynamics.
Okay.
Specifically, what happens when you have fluid flowing past a stretching sheet.
A stretching sheet. Interesting.
Yeah, so this might sound a little theoretical,
Yeah.
but it turns out this type of scenario is really important. It actually pops up in a bunch of real-world industrial processes,
Huh.
like when they're making plastics or textiles.
Oh, interesting.
And
Okay.
it can even help us, believe it or not, understand how some geological formations happen in nature.
Wow. Okay. So fluid dynamics, stretching sheets,
Yeah.
lots of applications.
Yeah, absolutely. So our mission today is to really dive deep into a research paper that tackles a really complex three-dimensional version of this flow problem.
Okay.
So we're not just talking about a sheet stretching in one direction.
Yeah.
This is the big leagues.
3D.
3D flow, exactly. And the paper we're looking at is called The Three-Dimensional Flow Past a Stretching Sheet and the Homotopy Perturbation Method by P. Donald Ariel.
Okay. The homotopy perturbation method.
That's the one.
Sounds complicated.
Yeah, it sounds a little intimidating, but don't worry, we're going to break it down. We're going to make it make sense. So the idea is, think of this as your shortcut to understanding some pretty advanced fluid dynamics. You don't need a PhD to follow along.
Right.
So one of the things that makes this whole thing even more interesting is that the simpler, the more basic two-dimensional version of this problem. So imagine, a sheet just stretching in one direction, not in two.
Right.
That actually has, I guess you could say, a pretty elegant, pretty straightforward solution.
Oh, yeah.
And it was discovered by Crane quite a while ago.
Crane.
Crane, yeah.
Right.
And it's referred to as the classical problem in the paper.
Okay. The classical problem.
So, folks have studied that 2D version pretty extensively. They've looked at, what happens if you add suction or magnetic fields or, different types of fluids.
So they've really gotten a handle on that 2D case.
Yeah.
It sounds like.
But where it gets really tricky and where this paper kind of jumps in is when you move beyond that simple 2D picture. So when the stretching isn't uniform, maybe it stretches faster in one direction than another.
Right. Right.
That's when things get really, really tough.
So you're saying this 3D problem where the stretching's kind of wonky, it's a lot harder?
Oh yeah, it's a whole different ballgame. And the paper actually says that this generalized 3D flow is governed by a BVP consisting of a pair of nonlinear differential equations.
Okay, a BDP, nonlinear differential equations. So for those of us who don't speak fluent math, could you maybe break that down a bit?
Yeah, sure. So BVP just stands for boundary value problem, which basically means you've got equations where the solution has to meet certain conditions at the boundaries of your system.
At the edges, okay.
At the edges, exactly. And then nonlinear, that just means that the relationships between the different factors, they're not simple and direct. They're kind of messy.
Okay, so not your nice straight line on a graph.
Exactly.
Yeah.
Exactly. So unlike, in the 2D case where sometimes you get these nice, clean solutions,
Right.
in this 3D scenario, you need some more sophisticated techniques, some heavy-duty math to crack it open.
All right, so that brings us to this homotopy perturbation method, or HPM, that this paper is all about.
Exactly. So the focus of the paper is really about figuring out if this HPM, is it up to the task? Can it handle this complex 3D flow problem?
Interesting.
So maybe just to get everyone on the same page visually, let's try to picture what we're talking about here.
Okay.
So imagine a big flat sheet, like a piece of paper lying on a table. And now this sheet is being stretched, but not in a nice, even way. It's being stretched. The paper tells us that the speed at which it stretches in one direction, we'll call that the x direction, is u equals x.
U equals x.
And then in the other direction, the y direction, it's v equals bi.
Okay.
And a and b, those are just constants. They tell us how fast the stretching is happening in each direction.
Got it.
And the fluid, the stuff we're interested in, is everything above this sheet.
Okay,
Yeah.
so we've got our sheet stretching maybe a little unevenly, and we're looking at the fluid above it.
Exactly.
Right.
Now, if we tried to just jump right in and use the fundamental equations that govern fluid motion, the Navier-Stokes equations,
Yeah.
if we tried to use those directly in this 3D situation, well, it would get really messy really fast.
I can imagine.
Yeah. So that's where this idea of similarity variables comes in. And this is something that a researcher named Wang actually came up with earlier.
Similarity variables.
Yeah. So think of these variables as I don't know, a clever way to simplify those really messy 3D equations into something more manageable. like ordinary differential equations.
Okay, so like a way to sort of reduce the dimensions of the problem without losing the important stuff.
Yeah, exactly. It's like taking a complicated 3D blueprint and finding a way to represent it as a simpler 2D drawing.
I like that analogy.
Yeah, so the paper, it shows these simplified equations. There are equations 4 and 5 in the paper.
Okay.
And they involve these functions, f and g.
Okay.
And they depend on a single variable, which is the Greek letter eta. It looks like an N.
Eta. All right.
Yeah, eta. And, we don't need to get bogged down in the specific math here.
Right.
But the important thing is that these equations, they capture the essence of how the fluid is flowing when this sheet is stretching in this way.
So it's kind of a simplified model, but it still captures the key features of the flow.
Exactly. Exactly. And then along with these equations, we have what are called boundary conditions.
Boundary conditions.
Yeah, and those are in equations 6 and 7 in the paper. And these conditions basically tell us what's happening right at the surface of that stretching sheet.
Okay.
Where eta is 0.
Right.
And what's happening very, very far away from the sheet as eta goes to infinity.
Okay, so like the edges of our system, right? Like
Yeah.
you're saying with the BVP.
Exactly, like the edges. So for example, right at the sheet, the fluid, it has to move at the same speed as the sheet is stretching.
Right, that makes sense.
And then far away, way out there, the fluid's basically still.
So it's all about how that fluid is moving and changing between those two extremes.
Right. And one more thing to point out here is this parameter, the Greek letter beta.
Beta.
Yeah, it's just B divided by A. So those constants that tell us the stretching rates.
Right.
And this beta, it basically tells us the relative strength of the stretching in the A direction compared to the X direction.
Okay.
And it turns out this is a super important factor in how the fluid actually behaves.
So it's not just the fact that it's stretching, it's how it's stretching that makes a difference.
Precisely. Okay, so that's kind of our setup.
Brilliant.
We've got the stretching sheet, we got the fluid above it, and we have these simplified equations, boundary conditions.
Yep.
Beta telling us all about that relative stretching.
Okay.
Now let's dive into this homotopy perturbation method, this HPM, that Ariel's paper is really digging into.
Okay, let's do it.
So, like we said earlier, it sounds a little intimidating, but at its core, it's a pretty ingenious idea.
Okay.
So basically what it does is it introduces this special mathematical kind of helper.
Helper.
Yeah. It's a parameter, usually called P.
P.
And P can smoothly vary from 0 to 1.
0 to 1. Okay.
Yeah. So imagine it, I don't know, like a dimmer switch
Oh,
for complexity.
I like that.
So when P is set to 0, our original tough equations, those nonlinear ones,
Right.
they transform into something much simpler.
Oh, okay.
Something that we can actually solve directly.
So we're turning down the complexity, making it easier to solve.
Exactly. And then as we slowly turn up that dimmer switch, as we increase P towards 1,
Okay.
the solution to these simpler equations, it starts to change. It starts to evolve.
Right.
And hopefully when P finally hits 1, we've landed at the solution to our original complex problem.
Oh, I see. So it's like we're gradually adding back in the complexity, but we're doing it in a way that we can manage.
Yeah, it's like, I don't know, learning to ride a bike with training wheels.
Okay, yeah.
You start with that extra support, and then you slowly take it away as you get more comfortable.
I like that. So we're slowly weaning ourselves off those training wheels until we're riding on our own.
Exactly.
With the full complexity.
Exactly. And the paper mentions that in HPM, the things we're trying to find, those functions f and g, they're actually expressed as a series of terms that involve increasing powers of this P parameter.
Okay.
It's equations 12 and 13 in the paper if you want to see what that looks like.
All right, so we're basically building up our solution piece by piece, adding in more detail as we go.
Exactly. We're making a series of smaller and smaller adjustments to our initial simple solution.
Okay, so that's how HPM works in general. What are some of the benefits of using this method?
Well, one of the big benefits that the paper points out is that HPM can often give us more elegant solutions.
Elegant solutions.
Yeah, compared to other methods that try to approximate the answer.
Okay.
And it can do this without sacrificing accuracy.
Oh, that's impressive. So it's like, it's not just a brute force approach. It's actually finding a more elegant, more insightful way to solve the problem.
Yeah, it's kind of like finding a clever shortcut. And the author, Ariel, he actually mentions the work of J.H.E. Yeah, who's really the pioneer, the guy who developed HPM. And he used it to solve all kinds of equations, from basic algebra to those complicated partial differential equations we were talking about earlier.
So it's a pretty versatile method then.
Yeah. His work has shown that it can be really powerful in all sorts of areas of science and engineering.
All right, so Ariel is using this powerful, elegant, versatile method
That's right.
to tackle this 3D stretching sheet problem.
Yeah.
So how does he actually go about applying it? What are the steps involved?
Okay, so the paper starts by taking those original equations that describe the fluid flow. Those are equations 4 and 5.
Right.
And it rewrites them in a way that's more HPM friendly, you could say.
Okay.
And this involves introducing another special kind of helper called an auxiliary parameter.
Another helper. Okay.
Yeah, and they label it B.
P.
And it's introduced along with our homotopy perturbation parameter, P.
Right. P, our dimmer switch.
Exactly, our dimmer switch. So that gives us equations 10 and 11 in the paper. And introducing this B, it turns out to be a really crucial step in making this whole HPM thing work for this problem.
Okay, so we've got our equations set up in this new form. What's next?
Right. So the next step in HPM is to look at what's called the zero-order system.
The zeroth order system. Okay.
Yeah, and that's what we get when we set our perturbation parameter, our dimmer switch, P, to 0.
To 0.
Yeah.
Right, back to the simplest version.
Exactly. So when we do that, those reformulated equations, equations 10 and 11, they become a lot simpler.
Okay.
They become equations 14 and 15.
Right.
And those simpler equations, along with a simplified version of our original boundary conditions, equations 16 and 17,
Right.
those can be solved relatively easily to give us our first guess for F and G.
So it's like a rough draft of the solution.
Yeah, like a rough draft. And those initial guesses are called FO0, and G0 and G0.
And the paper gives them an equation 26.
Okay, so that's our starting point. But I imagine we need to refine it to get closer to the real solution.
Absolutely. So these zeroth order solutions are just that. They're a starting point.
Right.
And how we refine them is we plug those initial approximations back into those original, more complex equations.
Right.
Okay.
And that creates what's called the first order system.
The first order system.
Yeah, and that's equations 18 through 21 in the paper.
Right.
And when we solve that first order system, that gives us the next level of approximation, which we call F1 and G1.
F1 and G1. Okay.
And those are given in equations 27 through 29. So essentially what we're doing is we're finding a correction to our initial rough draft, making it more accurate.
Okay, so we're adding more detail, refining the picture.
Exactly. Now, the paper mentions this crucial step that involves that auxiliary parameter B we talked about earlier.
Oh, right. B, the other helper.
Yeah, the other helper. So this is where the, I guess, the real elegance and power of HPM really shines through.
Okay, I'm intrigued.
So the guy who developed HPM, he suggested that this auxiliary parameter B, it needs to be chosen really strategically.
Strategically?
Yeah, and that's because it helps us get rid of something called secular terms in the solution.
Secular terms. What are those?
So those are terms that can cause our solution to become, well, unrealistic.
Unrealistic.
Yeah, they can even cause it to blow up to infinity as that variable eta, as it gets larger and larger.
So they're kind of like, I don't know, mathematical glitches in the solution.
Yeah, like glitches, exactly. So in this specific problem, those problematic terms, they look something like eta multiplied by an exponential function. It's eta times e to the minus b eta.
Okay, eta e to the minus b eta.
Yeah. So by picking the right value for b, we can actually eliminate those glitches and get a solution that behaves much better, much more accurately.
So it's like we're fine-tuning our solution to avoid those mathematical pitfalls.
Exactly. And in the paper, Ariel actually sets b squared equal to 1 plus beta, equation 30 if you want to see it.
Okay, so that's how he gets rid of those secular terms.
That's how he tunes out the static.
All right, so after all that, we arrive at these first-order approximate solutions.
We do.
For F prime and G prime.
Yep.
Which tell us about the fluid's velocity in the x and y directions.
Exactly.
And for F plus G, which has something to do with the velocity in the z direction.
Right. And those are equations 33, A, B, and C in the paper.
Okay, so we have our solutions. How do we know if they're any good? How do we check if they're accurate?
That's the million-dollar question, right? So the way we check the accuracy of any approximate solution is to compare it to solutions that we already trust.
Makes sense.
So in this case, Ariel compares his HPM results with an exact solution that he actually obtained in a previous publication.
Okay.
It's reference 29 in the paper, if you're curious.
So he has a baseline to compare against.
Exactly. And he also compares it to what's called a regular first-order perturbation solution that was obtained by Wang.
Wang, right? We talked about him earlier.
Exactly, and that's reference 23 in the paper. So this gives us a benchmark to see how well HPM stacks up against other methods.
Right, like comparing a new recipe to an old family favorite.
Exactly.
Okay, so what specifically is Ariel comparing in these solutions?
So the comparison, it focuses on these things called minus f double prime of 0 and minus g double prime of 0.
Minus f double prime of 0.
And minus g double prime of 0.
Okay, those sound like pretty specific mathematical terms.
They are, and they're important because they represent something very real. They represent the shear stress or the friction
Okay,
at the surface of that stretching sheet.
at the sheet, right?
Yeah, so in the x and y directions, respectively.
So it's like the drag that the fluid is putting on the sheet as it stretches.
Yeah, exactly, like the rubbing, the resistance.
Got it.
And by comparing these values, calculated using the HPM solution, with the values from those other solutions, we can see how well HPM predicts these really important physical quantities.
Okay, so we're looking at how well HPM predicts this shear stress, this drag on the sheet.
Precisely. And the paper has this table, table 1, that shows these comparisons for different values of beta, that ratio of stretching rates we talked about.
Right, beta. So what does the table tell us? How does HPM perform?
So what's really cool is that the table, it shows that HPM, it gives results that are much more accurate than Wang's first-order perturbation solution.
Okay.
Especially as beta, as that ratio of stretching in the y and x directions, as it gets larger.
So the more uneven the stretching, the better HPM does.
Yeah, exactly. Now, Wang's solution, it actually does a pretty decent job when beta is small.
Okay.
Which makes sense because that's kind of what it was designed for.
Right.
But as beta increases, its accuracy, it just tanks. It really drops off.
So it's kind of limited in its range.
Yeah. But HPM, it holds up much better. It doesn't have that same drop in accuracy.
So it's more robust, more reliable across a wider range of conditions.
Exactly. And that's one of the key advantages that the paper highlights. HPM, it can provide what they call a uniformly accurate solution for all values of the physical parameters.
Wow. Okay.
And in this case, that key parameter is beta.
That's impressive.
Yeah.
So it's not just giving us an approximate solution, it's giving us a good one.
Right. It's not just an answer, it's a reliable answer. And that's a big deal.
Yeah, that's huge. It means we can trust HPM to give us good predictions no matter what the stretching situation is.
Exactly. So to wrap things up, the paper concludes by emphasizing that HPM, it's a really valuable method for solving these complex fluid flow problems, especially the ones with multiple nonlinear differential equations like we have here.
Right.
And the author points out that in this specific 3D flow problem, the fact that those two main equations were pretty similar, that allowed them to use a single auxiliary parameter, that b.
Right.
But they suggest that in the future, research could look at applying HPM to problems where you might need more than one of those auxiliary parameters.
Oh, okay.
Which could be really interesting, right?
Yeah, it could open up a whole new world of problems that we could tackle with HPM.
Exactly. So to kind of bring it all home for our listeners, what would you say is the main takeaway from our deep dive today?
Well, I think the biggest takeaway is that this paper, it shows us just how powerful and elegant this homotopy perturbation method, this HPM, can be.
Right.
It can provide really accurate solutions, even for those tough three-dimensional fluid flow problems that we've been talking about.
Right. The ones with those messy nonlinear equations.
Exactly. And that's important because it gives us a way to understand and predict these systems without having to rely only on, computer simulations, which can be really time-consuming and sometimes obscure the underlying physics.
Right. It's like HPM, it's giving us a shortcut to understanding the fundamentals of how these systems behave.
Exactly. It's giving us insight, not just numbers.
Exactly.
Yeah.
So for our listeners, I think this highlights that these mathematical methods, they're not just some abstract theoretical exercise.
You're right.
They can provide really accurate and useful insights into all sorts of real-world scenarios, from how we manufacture things to how the natural world works.
Absolutely. And it makes you wonder, if HPM can do this for fluid dynamics, could it be applied to other complex systems?
Yeah.
Like, could it help us understand how materials behave under stress or how biological systems work?
That's a great point.
It really makes you think about the potential of these mathematical tools to unlock secrets in all sorts of different areas.
Absolutely. It's about seeing beyond the surface, appreciating the power of math to help us make sense of the world around us.
Couldn't have said it better myself.
Well, on that note, thanks for joining us for another deep dive.
It's been a pleasure.